Thank you very much for having me and lasting it out until this late. Look, we're talking about making qubits from transistors. That's the kind of short story. There's pages of blank text for you to read. There's oscillations, coherent oscillations in transistors made at a 300 millimeter wafer scale, so slightly more interesting. And there's even a slide with some Paleozoic marine animals. So hopefully something in there for everyone at this stage of the day to keep us moderately awake. A page of blank text, right? The best way to start any presentation, but it makes an important point. You know, back in the 50s, this was the state of the art. This was how they were realizing computing, and this guy was probably getting as much hassle as I've got over the past 5-6 years. We don't talk an enormous amount because most people's reaction when you come out and say, we're making qubits using silicon spins, then what, for the past 6 years, people said, well, where's your 2-qubit gate? And that's a reasonable thing to say. And over the past year, 18 months, we've been able to address that. We've seen a lot of really nice realizations of 2-qubit gates in silicon. And we've already heard talks about why you would want to do this in silicon. There's a lot of other really nice things you can do in silicon, like low noise amplifiers and multiplexers and making very, very, very large systems. But it always comes back to, have you fundamentally made a really nice 2-qubit gate? Was that actually in 300 millimeter silicon made in a foundry, or was it in silicon germanium or something which is a little bit more exotic, even by our relatively low standards? So that's what I wanted to show you today. It's just a very brief summary of who we are, because we don't really talk an enormous amount. We mostly kind of keep our heads down and do some physics in a lab in London. And I wanted to show you an update on that, who we are, and maybe just excite you a little bit about the prospects for silicon quantum computing. Because if I was more of a showman, then I'd probably get out a chip and be like, look at that, there's 1 million qubits on there. But I'm not, because that would be a lie. There'd just be millions of transistors that we might want to make into qubits, and that we've shown some really nice 2-qubit gates with recently. So instead, that's what I would like to show you today. And here's the marine animals, because this is basically where we are. We are in the Paleozoic era in quantum computing. We've come out from small cells, and now these small cells are coalescing, and we are still millions of qubits from something intelligent. But I hope that this small trilobite will gradually evolve over the next year, several years, into something that is actually going to be showing some intelligence. And I have a lot of respect for these other Paleozoic animals as well. So this is who we are, because as I said, I don't expect a huge number of people will know us. We were founded in UCL and Oxford by John and Simon. We were joined recently, a couple of years ago, by Alberto Sangiovanni Vincentelli, who founded Synopsys and Cadence. He, like me, had some serious issues with quantum computing when we first got invited into this field, but he said, what, if you can do it in CMOS, then I'm on board. That's really exciting. And we've grown this a lot over that period. So, I joined 6 years ago. We're now about 55, 60 people based in central London, and you're very welcome to come down and join us. We're just above King's Cross. And we raised decent amount of money earlier on this year from Porsche and Bosch and Sony, because we showed that you can indeed make a good 2-qubit gate using just a 300 millimeter natural silicon process. So we've got a long way to go, but we've come a long way as well. So this is the vision. I think I was perhaps slightly downbeat in saying where we are right now in the Paleozoic era, but actually these are revolutionary devices, and I'm incredibly excited about this. I wouldn't be here doing this if I weren't. But they're also incredibly hard to build. Building things that actually scale and go beyond a small number of kind of test devices is actually very, very hard. And that's why we're doing it using the process that we'd show off to aliens if we could. This process that makes 57 billion of anything without actually making mistakes is pretty awesome. And the modern transistor hasn't really changed in 20 years. It's on the order of about 20 nanometers or so. And how this would ordinarily work with a transistor. You know, you suck up, what, about 3,000 to 5,000 electrons under that central gate there, and that allows your current to flow. And all that we do is make minor adaptations to that same transistor. These are made with standard tier 1 foundries, so we work with global foundries and with IMEC in doing some more bespoke adaptations around the doping. And we reduce the voltage, so we can get a single electron under there. And then we use the spin property of that electron to realize qubits. You bring them closer together, and you can perform operations. And I'll show you a little bit about that in the slides to follow. But this does a lot of things, and it's not just on the qubit side. So I also want to show you that. I think this is an earlier version of the slide, so I may well flick through that. Yeah, okay, never mind. But I wanted to show you essentially 3 things. So it's not just the qubits, but it's all of the ancillary circuits that go alongside them. So using this kind of approach, where most people would have thought we were, 2, 3 years ago, was in etching individual structures, which we can then, trap single electrons under and perform this, radio frequency readout, whereby you can tell whether you've got a single electron under the gate in your transistor. And this was nice, but it wasn't the kind of scalable, let's use CMOS process that I think we all would like to be at if we were really leveraging the power of CMOS. Whereas where we've got to and what we published on over the past couple of years, is this kind of chip. So this was our Bloomsbury chip. This had, say, 3 million transistors, but this wasn't all qubits. I'm not going to tell you as 3 million qubits. What there was, you see a pointer? No. So in the sort of bottom left there, you can see 3 green boxes and then a larger green box. Each one of those is 1,024 quantum dots. So you can address each of those in a nice crossbar array. Say this was made using a standard process at Global Foundries. It has digital addressing, so you can control every single one of those 1,024 quantum dots using just 5 voltages in, and you can raster scan them all. And in the readout chain of that, you can have a low noise amplifier as well, all operating at millikelvin temperatures. So the power dump of this thing is about a couple of hundred nanowatts. You can have low noise amplifiers, you can have multiplexers, you can have digital circuitry. Anyone who's a IC person will probably recognize the nice ring oscillators down there in the bottom right-hand corner as well. And the best thing that I think we've done at Quantum Motion is bringing together people who know about the quantum side, the qubits, how to realize these things out of transistors, and putting this together with a lot of very impressive circuitry that operates down to these millikelvin temperatures. And so this is what I wanted to show you is, how does this help us to then show that we've got some quantum operations? And so I wanted to take you through kind of how do we quickly scan through thousands of devices to demonstrate that we have very nicely controlled quantum dots. How do we then read them out with incredibly high fidelity? And then how do we make sure that from that very high readout fidelity, we can determine that we have very good control over individual and 2-qubit gates. But we'll start with the mass characterization, because I was really pleased with this. We only decided to do a press release on it when we saw that Intel had a really nice result saying that they'd read out 900 quantum dots with some wafer probing. And we'd done this on an integrated chip, so I thought, it's worth doing, because theirs was 900 quantum dots in about 24 hours. And my team had done 1,024 quantum dots in 5 minutes. And this was all on an integrated chip. So just bonded up, top of the fridge, and we could get these diagrams over to the side. We had a machine learning algorithm that would detect where we had a single electron. So you kind of work back in your voltage space to the point where you saw your kind of last crossover. No, yep, I've got 1 electron underneath my transistor. And we'd raster scan through 1,024 of these and recognize which one's the best one in a time scale of 5 minutes. So here's a little bit more on that. There's a kind of a zoom in on the structure and how small it was. So this was about a 3 by 3 millimeter chip. and a farm of 1,024 quantum dots, all addressed with word and field lines in a standard kind of CMOS addressing way, and all of this multiplexing happening down at the lowest stage in your dilution fridge. It's all happening at 10 millikelvin. And this is in preparation for publication. We've kind of put out an early release on the archive, but anyone who's interested in some really neat electronics and quantum physics, I'd thoroughly recommend you read this, because, again, if I was a bit more of a showman, then I'd be like, 1,000 qubits on a chip. But no, the purpose of this was really to demonstrate that you can move several orders of magnitude faster. You can put lots of different kinds of designs for really good quality qubits, and you can scan through them and work out which one's the best, and then iterate and do another tape out and another tape out. So this was really the purpose of this particular chip. And it really did allow us to move on to then another demonstration. So here we do have one of the older examples, but we repeated this in that previous chip as well, whereby we showed that then by putting two of these devices together, so a transistor where you did have a single electron quantum dot, and another one where you'd be reading out from it, essentially showing that you can detect the difference, the capacitance of these two electrons next to each other. You can run a radio frequency signal between them and try to oscillate one electron between your two transistors. And from that, you can measure a difference in your radio frequency response. And so it's an incredibly compact and fast and high fidelity method to determine whether or not you have an electron and in which direction the spin on that electron is pointing. So this was an incredibly important result, going from firstly saying we have a large number of these things, we can show that we can prepare single electron quantum dots in them. And then the next step here is we have all of these single electron quantum dots, and we can determine which way up the spin is pointing with incredibly high fidelity. And so then the next step beyond that is, okay, maybe we can work out how to do an entangling gate with that. And so here what we have is not just saying that we have two electrons with different spins next to each other, and I can pass a radio frequency signal between them, and I can oscillate them back and forth and then just determine whether their spin is up or down. But I can actually firstly prepare these things. This is what this diagram here is. So this is, what's my voltage on my gate 1, what's my voltage on my gate 2. If I change this voltage slightly, I'll bring both of these electrons onto the same gate. I'll separate them, and thanks when they're on the same gate to Pauli's exclusion principle, we know that they're one spin up, one spin down. We'll separate them, so that's going across this kind of voltage line from 2, 0, where they're both on one transistor, to the other side, where they're now separated, 1 and 1 on either transistor. And then we can let one process. So both of them are now processing in space, and then we'll bring them back together again, and then we'll do a measurement. The same measurement that we showed above had a readout fidelity of 99.2%. And this is the basis of the entangling gate that we've shown. So this was on a natural silicon wafer, made at the 300 millimeter wafer scale, and it was fast. This was a 7 nanosecond entangling gate, and yes, it was a T2 star of 500 nanoseconds. That's not enormously long, but this is natural silicon. It can go orders of magnitude faster than that, but you need to start with what can I actually do just in a standard foundry with natural silicon. And this is what we got. So you go back to the original diagram. 2 electrons separated, let one process, let it process for a certain amount of time. That's up the axis on that left-hand side. And then measure it after certain amounts of time. See whether when you put these two things back together again, whether you actually get a signal. And this shows you, am I still coherent? Have I still got my quantum information there, or has it all sort of decayed into the ether? And so you've got a very, very long T2 star. That's kind of, when you no longer have any signal from this, and you've got a very, very fast oscillation. That's how, the period between the dark and the light here, that's, it's going around 1, we're putting it back onto each other, and you can read it out and either get a signal or you get no signal. And this is what we're demonstrating here, is that, in natural silicon wafer, you can not only read out, you can not only make these things with thousands of them on the same chip, but you can also perform an exchange operation. And this and the work that preceded it and the work with global foundries, this was the basis of why we got in a decent amount of cash from some investors, and why they and me were just so excited about the promise here, because we're no longer talking about maybe doing this or the promise of CMOS, but if only we had this. It's been proven now. So yes, there's a long way to go, but we have integrated control electronics and quantum electronics and digital readout all on the same chip, which to me, that should be the answer to how can you make millions and millions of qubits and actually then be able to do something very interesting in a quantum computer. So maybe I've got time just to then go along a little bit more, because we're not just a hardware company. So how do you use these things? So this is what Simon Benjamin does in the company. All of the kind of preceding stuff, that was John and Fernando and others who've worked at UCL and brought this out from decades of experience in terms of reading spins in quantum dots. And what Simon does in the company is says, well, okay, let's assume we do have very, very good quantum dots. How much longer do I have? Is that it?
You can wrap up.
I can wrap up. Brilliant. No, this is pretty much the last slide. But this is what Simon does. It essentially says, let's assume we do have a really, really great entangling gate. What's the best thing that we can do with it? And the answer is make a large fault-tolerant quantum computer. So here we're saying, let's put each one of these entangling operations at the corner of a little racetrack. And let's move our quantum dot, or our electron, around that racetrack and let it entangle at each corner, move it on, entangle, move it on, and then read out. And that's the basis of a surface code that not only works in 2 dimensions, but actually, because you can have multiple different electrons going around this racetrack and only interacting with the same, helpfully colored other electrons on there, it actually forms the basis of a sort of quasi 3D code. So you can talk more on that. That's probably a good point to wrap up, but long story short, is the silicon revolution again. So yeah, with that, thanks very much for your time.